All right, hi everybody. I'm Angela. I'm a deputy PI for the Mini-RF radar on LRO. And I just wanted to give you all an update on, whoa, it's moving. That's going to be fun. On some of the new data products that we have and available, and also sort of the radar data availability at the polar regions for doing some of this landing site analysis. So radar data is really important in landing site characterization and for landing site support. It has a very long heritage across the solar system, particularly on Mars. You can see here, this is an Arecibo image of the InSight landing region on Mars, and it can tell you a lot about the surface properties, the roughness, where there might be boulders, and it gives you things on information on the size ranges and scales of the radar wavelengths. So depending on what radar you're using, you get different types of information, and it can tell you a lot about surface rock distributions or subsurface rock distributions, because radar will penetrate into the surface as well. It can tell you about the morphology, both surface and subsurface. And also what's really important for landing site support is it can tell you, ground-based and orbital radars tell you a lot about the radar reflectivity of the surface. And radars are often used by descent systems. And so having an understanding of what that terrain looks like is really important to understand how your descent system will work. And we know that it's been used successfully on Mars for the rovers and InSight. And so, of course, we can translate that sort of experience to the moon. So today I'm going to talk about Mini-RF. It is the radar on board the LRO spacecraft. There are other orbital radars, of course. We had Mini-SAR on Chandrayaan-1. There's the DF-SAR radar on Chandrayaan-2. And we also have ground-based data for the near side of the moon. But Mini-RF was a dual frequency radar, both at S-band and X-band. And so that's about a 12.5 centimeter wavelength and a 4 centimeter wavelength. And we transmitted a circular pulse to the surface and received the radar backscatter in both horizontal and vertical polarizations. And this allows us to do a lot of interesting things with the data. So we can provide general backscatter information, but also a number of daughter products that provide information about, as I said, roughness and other morphological characteristics of the surface. We have operated in 2 different configurations. So we started out as a monostatic radar, which meant that the radar, this is fun. The monostatic radar transmitted and received the data. Unfortunately, a few years into the LRO mission, our transmitter died. And since then, we have been operating in a bistatic configuration where we use ground-based radars on Earth to transmit a signal to the moon and receive the backscatter at the spacecraft. And our 2 wavelengths will give you information about the surface and also sort of integrated information about down to about a meter or so into the surface of the moon. All right. So when we're looking at the radar data, it's really important, of course, to understand what it is that it's telling us, right? We're very used to looking at images. We understand sort of intuitively what that means. But because radar is a much longer wavelength, it's telling us about things that are, bigger in scale. And so this little cartoon here, oh, I have no mouse. Okay. Shows you a little bit about, the different colors on this are different, wavelengths of radar, and the different colored rocks and things would be the things that radar would see. And so if you use multiple different wavelengths, you get a lot of information about things at multiple different scales, which can be very important when you're looking at landing sites or, scientifically, but it can tell us a lot about small boulders and big boulders, or, the distribution of those different things. It can also tell us about bulk dielectric properties of the regolith, which is really important for understanding things like density or volatiles, because the radar will interact differently with the regolith in different cases. And it provides access to PSRs, right? We, Prashun showed some really nice images of long exposure NACs or the new shadow cam images, but radar is its own illumination source, and so it can see just inherently into the PSRs, and we have images of them from the Mini-RF radar that are available. All right. So I'm going to show you briefly kind of what the availability is. For the monostatic data, we captured about 98% of the lunar poles. As you can see here, all this data is available on the PDS, but also on QuickMap. So we have data down to 2,048 pixels per degree, which is available on QuickMap. In general, we give out the 30-meter data because it's a little bit less noisy. You can see here, we have basically coverage of the entire pole in S-band, and a lot of the pole in X-band. X-band data is a little bit less of a resolution. And you can see here, this is compared to the Artemis landing sites. And so we have very good coverage of all of the Artemis landing sites in the monostatic data. If you add in the bistatic data, it's a little bit trickier to get at the poles. And so we have less coverage, but we have pretty decent coverage of the Artemis zones as well. And they are, again, slightly lower resolution because the data is a little bit noisier. Here's an example of one of those collects. So this is a strip here. You can see it's been corrected for topography that covers basically the South Polar region. And you can see the place that I've highlighted here. That is the Hayworth Artemis zone. And the stuff that looks very streaky is radar noise because it's on a slope that the radar couldn't see from the Earth, but you can see the floor of the crater really nicely in the morphology here in the data. We also have some newly reprocessed data that is starting to pull out a lot more information and correct for some things that radar is just sort of inherently difficult with. We have orthorectified and correctly seleno-located mosaics that are available on QuickMap. And recently we have performed an incidence angle correction on these to enhance differences between different regions, but also suppress the variability due to slopes. That is something that is difficult with radar. Radar facing slopes, you'll tend to get more backscatter than non-radar facing slopes, and so you kind of have to be careful. But if you correct for that, you can start pulling out a lot more differences, and you can see here's an example of a product that Caleb Bassett has created. This is an S1, which is essentially the power return to the radar. And if you look at CPR, which is probably what most people are used to looking at, that's the roughness parameter. You can start to see very, very big differences that are being pulled out from the radar data at the poles. So these are in the process of being published, and we will make them available to the community. I'm going to run them through a few, just to give you some ideas of what this looks like. So here's the Malvert Massif Artemis zone. You can see the Lola DTM on the side there. And then our normal mosaic in the middle, you can see that kind of red region, and that's a radar facing slope, or it's like noisy. And so you get this sort of like artificially enhanced CPR. But if you correct it with the new products, you can start to see the actual differences in the terrain and the roughness due to small craters or boulders. And you can do this for the different zones. So this is Faustini Rim. And you see just this beautiful blocky ejecta around this small crater. You can see streaks and different sorts of roughness, things that are happening due to the local geology and the craters that are there. Again, just running through these, you guys have an idea. The Gerlach and Hayworth are a little bit less rocky, a little bit less rough, but you can see these small craters and their ejecta. And these are all things that you would want to pay attention to, right, in landing site characterization. You can find them in the radar. You can then go look to see if there's NAC images and do boulder counts, things like this. It provides you a really good regional view. The other new product that we have has been normalized to the opposite sense polarization coming back, and it's pulling out a lot of interesting things at smaller kind of roughness values. So you can see here, this is a ray actually from Tycho crater that we have found crossing the South Polar region. You can see these streaks and secondary ejecta coming from Tycho. Oh gosh, come on. You can see that on the farther down, you get these sort of, they look like wind streaks, but it's the moon, so they're not wind streaks. But these really interesting patterns, and these are all things that would be very interesting scientific targets, if you were to land near them and provide new information to help us pick, between places on the moon. And I'll leave this here. This is a summary of where we have data in the Artemis regions. We have coverage from all of the monostatic, and we're working on the bistatic data. If there's something that you guys need, we are still collecting data. Please reach out. If you have questions about the data, please reach out to us. We are more than happy to help you. We would love for people to use the data. That's it.